Hello everyone, tonight we'll be starting on Unit 2, and Unit 2 is Statics and Dynamics. For today, we're going to look at this idea of a force. In order to do this, we're going to look at a situation where Galactus, the eater of planets, is going to play tug of war with the Flash. Of course, we're using an adamantium cable. That way, it won't break. So I know what you're saying. Hold on. So the Flash is the Flash. He's not very strong. But in the game of Tug of War, we only care about the force that someone can exert. So let's look at what it means to exert a force. So Newton's second law, we'll learn about the other two later. But Newton's second law can be written as an equation, and it goes like this. F is equal to ma. So F is naturally the force, m is the mass, and a stands for acceleration. So force is equal to mass times acceleration. Let's just look at units briefly. Mass, remember, is measured in kilograms, acceleration in meters per second squared, and this unit of kilograms times meters over second squared, that's the same thing as 1 Newton, or 1 capital N. 1 Newton. If I have a car and I apply a force on this car, if I apply a force on this car or a force on this mass, I'm going to cause it to accelerate, as long as I am pushing or pulling on it. So I apply a force on the mass, it causes it to accelerate. When I stop pushing or pulling on it, the car will go off at a constant velocity. It won't accelerate anymore. Okay? So we know that if we can push or pull with a large acceleration, we can exert a rather large force. So we need to figure out how much force the Flash can exert on Galactus. So here's Galactus, here's the Flash. We want to figure out how much force the Flash can exert on Galactus. Force. So when we do problems in physics, remember that we always start with a picture. So when we're looking at forces, we draw what is called a free body diagram. So here's the Flash, here's Galactus. We're going to represent Galactus as a single dot. Okay? These are called free body diagrams. So we're going to represent Galactus as a single dot. And we are going to draw an arrow or a vector indicating the force that is being exerted on Galactus. So in this case, the Flash is exerting a force on Galactus to the left. So we can draw an arrow to the left. And we can call that force from the Flash. Okay? So now the next step, as in any physics problem, we need to write the equation of force. So we know that F, from Newton's second law, F is equal to mass times acceleration. So I've looked up the mass of Galactus for you, and that is 16,000 kilograms when he's in his smaller form. And I've also calculated the acceleration of the Flash. From a video that I watched online, he can go from 0 to light speed in about a minute. Here we get an acceleration of 5 times 10 to the 6th meters per second squared. That's the acceleration that the Flash can exert. Now I'm assuming the Flash can keep this acceleration even when he's pulling on Galactus, which is a rather large assumption. Let's take these values and let's use them to find the force that the Flash can exert. So the mass is 16,000 kilograms times the acceleration, which is 5 times 10 to the 6 meters per second squared, and we get a force that the flash can exert of 8 times 10 to the 10th newtons. That is the force that Flash can exert on Galactus. Now let's return to the tug of war problem. Now Galactus is going to start pulling back on the Flash. Alright, so first let's look at the static situation where Galactus is going to exert a force equal and opposite to the force that the Flash exerts on him. So, this is the static situation. So let's draw the free body diagram. So here's our situation represented by a single dot. The Flash can exert a force of 8 times 10 to the 10th newtons. And if Galactus is pulling in the opposite direction with the same force, we can call that force of Galactus is also equal to 8 times 10 to the 10th newtons. So if they're both pulling on each other with an equal force, well, what's going to happen? Physically, what is going to happen? Well, let's look at my Hot Wheels car one more time. So if I apply a force on it to the left, I will cause it to accelerate. We know that. If I apply a force on it to the right, it'll cause it to accelerate to the right. If I apply two forces on it at the same time, it may go left, it may go right, but if both forces are equal, that car is not going to move at all. Just as if I were not applying any force on it at all. So this is a static situation because this car, it's not moving. It's an equilibrium, we call it. So a force this way can match an equal force going the other way, and the car cannot move. Now as soon as one of the forces overcomes or becomes greater than the opposite force, the car begins to move, and we have what's called a dynamic situation. And dynamic means that it is moving. So, let's say Galactus eats a planet like he eats an apple, okay? Well, in this case, let's have him eat a Swedish fish. So, as a result of Galactus eating a planet, let's say now he's able to exert a force of 8 times 10 to the 11th newtons. Okay? And let's say that the Flash can only still exert a force of his 8 times 10 to the 10th newtons. The question is, who's going to win the tug of war, and what will be their acceleration? So, we already drew our picture. Now from our picture, we need to pull out an equation. The equation being F is equal to mass times acceleration. Okay? But I'm going to alter this F just a little bit because now we're dealing with more forces. Okay? I'm going to draw the Greek letter. This is a Greek, This is a Greek letter called epsilon. And basically it just means a summation. You're going to take all of the forces that you have in your picture, and all you're going to do is you're going to add them up. Okay? So in this case we have two different forces here. So we're going to say that the summation of all of the forces, also called the net force, is going to equal, okay, well we have the force, starting to tip over here. We have the force of Galactus, and we're going to add the force of the flash. Now, we need to set up our coordinate system. So we're going to call this way positive, and this way we're going to call negative. Okay? So when we actually plug in these numbers, we're going to get the summation of all of the forces is going to be equal to the force of Galactus. Oh, here we go. The summation of the forces, of all of the forces, we're going to have the force of Galactus. So that's going to be 8 times 10 to the 11th newtons. And that's going to be added to the force of our flash. But notice that the force of the flash, this way is positive, is in the negative direction. So we need to make sure that we include the negative in there. And that's going to be 8 times 10 to the 10th newtons. Okay? And because this is a dynamic situation, the flash is going to be moving. Okay? Galactus is going to be pulling on the flash in the opposite direction. So this is going to be equal to mass times acceleration. And because the flash is being pulled, because Galactus is exerting a greater force, this needs to be the mass of the flash. Okay? So now if we run these numbers, you're going to get 7.2 times 10 to the 11th newtons, and that's going to equal the mass of the flash times the acceleration of the flash. Okay? So I'm assuming that the flash is maybe a little bit bulkier than normal, so we're going to go, he's 80 kilograms. We're going to make that assumption. Okay, so if we want to solve this equation, all we have to do is divide by the mass of the flash, and we're going to be left with acceleration is equal to 7.2 times 10 to the 11th newtons, divided by the mass of the flash, which was 80 kilograms, and that's going to give us an acceleration of 9.0 times 10 to the 9th meters per second squared. So, what does this mean? This means that in a situation of tug of war, when Galactus is pulling with a force of 8 times 10 to the 11th newtons, and although the flash is still pulling this way, his force of 8 times 10 to the 10th newtons, then the flash will accelerate this way, at 9 times 10 to the 9th meters per second squared.